Okay. The audio might cut out on this. The batteries were charging, which usually is an indication that the batteries are about dead, so I may need to have somebody go for batteries. We'll see. So, how y'all doing? You're sleep deprived now? You're in trouble. The exam is ready. It is posted, but inaccessible for you until class is over. It is set on a timer to be available at 12:30. So, therefore, as soon as class is over, you can go as a thundering herd to go to the nearest computer and download the exam. It is arguably the shortest exam I've ever given, including in-class exams. As shortest paper-wise, it's only 6 pages. As shortest problem-wise, it only has 3 problems. So anyway, we'll see how you like it. I think it's a fun exam. I hope you learn a lot. Arguably. All right, now you're getting it. Now you understand. You shouldn't be learning on an exam. What you will learn is you didn't know that you could do some stuff that you're about to do. Anyway, does anybody have any questions they want to ask? Comments they want to make? Rotten tomatoes they want to throw? Well, you bring the tomatoes next time. Garrett.
Would it be possible to write that in class, go through the exam a bit? Because some of your questions sometimes are a little confusing. So if you could just.
I would be happy to go over problems with you after you've had a time to digest them. I think that they will be much more effective once you've had a chance to look over the exam, read through the questions, then contact me. Yes, overcome your panic first, and then talk to me. All right, so you can decide where the panic halts before you can start the panic. All right, fine. The exam, logistically, the exam is open book, open note, open prior lecture, closed internet, and closed person, except for me and you.
Get on the Blackboard.
Blackboard, you can access anything that's on Blackboard.
Past labs are okay.
Past labs are fine. Okay. Your past labs are fine. Last year's labs are not fine. Okay. So logistically, the exam is posted on Blackboard. And it's posted as an assignment, just because that makes the grading easier. So when you submit it, you'll have to submit it electronically. So you're going to have to type your answers. You can submit C files, you can submit text files, you can submit PDF files. Do not submit Microsoft Word files, okay? And I've given you instructions in lab write-ups on how, if you want to use Word, fine, but you have to make it into a PDF file, and there are free utilities to do that. Don't send me an open office document. Send me a PDF if you want to use a word processor, okay? Or a clear text, plain text file. Other thing of note, those of you who happen to be U.S. citizens, Hill Air Force Base is desperate for people if you're looking for a job. It was an interesting experience. I went down there yesterday. Some of the guys listening online are actually Hill employees, but they have immediate openings for 50 people. They have probably within the next year maybe another 100 people they're looking for. These are electrical engineers, computer scientists. The guy that I was talking to said in particular he very much likes this idea of a computer engineering degree because it seems to balance the ability to do programming against the fiddleness that electrical engineers do. They like to get in touch and fiddle with hardware. So anyway, they are looking for people. All right. Today we are going to talk about Chapter 5. This material is not on the exam. But let me raise you this question. So Chapter 5 talks about reliability. The question is the above code reliable? Anybody want to take a stab at what this code does?
Dereferences null.
It dereferences null, and what does it do? What does dereferencing null do?
Throws an exception.
Okay, so what it does is it takes the number 0, casts it to be a pointer to an unsigned integer, dereferences it, and writes to that memory location 3. So what you're doing is you're writing to the address 0 the number 3 as a 4-byte quantity. Is that reliable? What's it going to do? So is this going to, if you built this code and ran it on your Windows box, what would you get?
The same thing every time.
Would it work? Would it work as expected? Is it going to write the number 3 into the address location 0? Okay, I've got all across the gambit here. I've got a yes, a no, and a maybe. I haven't gotten the answer that I tipped. Yeah, there you go. Okay. It depends. All right. How many of y'all vote this is going to work as expected? It'll put the number 3 at address 0. Okay? How many of y'all vote, heck no, this will never work, it's going to crash your program? How many of y'all vote, I have no idea? How many of y'all vote, Dr. Ames, why are you doing this to me? Okay. So, modern processors have what's called a memory management unit. And a memory management unit allows the operating system to configure which regions in memory are deemed accessible and are deemed inaccessible. Okay? It also facilitates a mapping between physical addresses in actual RAM and virtual addresses. So, if you recall from your operating systems class, or from 3720, or wherever you have had it, or if you haven't, your Wikipedia days where you should have been curious enough to look this up anyway. Virtual addresses, every process that runs on your computer thinks that it has access to 2 gigabytes worth of address space. It can access every address from address 0 all the way up to 2 to the 32 minus 1. Okay? So, or 2 to the 32 over 2 minus 1. Okay, so what this does, this attempts to access an address, and because it's dereferencing address 0, and this is a C program that runs, the address that it's attempting to address is a virtual address, because every process accesses virtual addresses. When you present a virtual address in a memory operation, it accesses in the memory management unit and says, what's the physical address? Where's the physical address that's associated with this virtual address stored in memory? Okay? So it does this address lookup. Why does it do this address lookup? Because of the paging that goes on. You're going to load a page of memory into a page slot in RAM. Okay? So that way, every process, the most frequently used set of blocks of memory that it accesses, those regions of memory that it accesses frequently, will be loaded in RAM. Everything else will be loaded on the hard disk. Okay? So when this process attempts to access address 0, it's not accessing the 0th address in RAM, it's accessing its address 0. Okay? However, the memory management unit has been configured on all modern 32-bit machines or 64-bit machines to say, you know what? Whenever you're accessing address 0, that's probably not right. That probably means that Mr. Programmer has made a mistake. Because Mr. Programmer has made a mistake, what it means is he's trying to dereference a null pointer. So I'm going to help out Mr. Programmer, and I'm going to throw an exception every time you try to access address 0. I'm going to mark that as, you can't have that. You can't access this address. So whenever you attempt to build and run this program, what will happen is Windows will pop up a box that says, unhandled exception, attempted to dereference an invalid address, or attempted to access null pointer, or attempted to access address 0. So it'll crash your program. The operating system will kill your program when you attempt to do this. This program will cause a crash. Under Cygwin or Linux, it will cause what's called a seg fault, a segmentation fault. Okay? You've had 3720 from me. You should very much know what those are. If you don't, then you can't remember. You ought to be embarrassed. Okay. So this program is going to crash. I've written this program right here. You write 3 to the address 0, it will crash. Is it reliable? Why does that, if it's going to crash, why does that mean it's reliable? So if you put a bug in your program and you observe the behavior of that bug every time the program runs, then you're saying your program is reliable?
Well, that's what you want the program to do. Yes.
What does reliability mean? So if you've got a bug in your program's reliable. That's what you're telling me. Okay, then let's define what bug means. Is bug expected behavior or unexpected behavior? It's unexpected. You know, if I want my program to run, if I define that as expected behavior, this program doesn't run. It crashes. So therefore, it deviates from what I expect. Why would you say if a program has a bug and you observe its behavior running every time, if that's what you expect, how is that a bug? Okay, if the bug's in there in the first place, then what you're saying is that bug's an error. It's a problem. It shouldn't be there. But if you expect it to be there, then you're saying it should be there, but it shouldn't be there. You are a logical contradiction. You cease to exist. Okay, should it be there or shouldn't it be there? Should the bug be there or not? Jonathan?
So, if you change the address for the access there, is that still an error, or?
If you change the address that you're trying to access, is it still an error? Well, what happens if this isn't exactly the program that we intended to write? What happens if we declared a pointer variable and set it equal to null, and then dereference the pointer variable and set the dereferenced pointer variable equal to 3? Well, it'll do the same thing because we're effectively dereferencing null because the pointer is initialized to 0. Well, what happens if now instead of having a pointer initialized to 0, we have a pointer set equal to malloc size of unsigned int, and we have that dereferenced equal to 3? Now we've removed the crash because we are no longer accessing an invalid memory location. The value of the address that we're dereferencing is no longer 0. It is now some address that we pulled off of the heap. Well, what happens if this is embedded in a huge old program where we've got, one guy went through and wrote all his code and accessed the heap, allocated a variable off of the heap, and then you dereference that variable and set it equal to 3 and everything's great. But what happens if somebody else later on goes through and looks at this code and sees a pointer there and says, oh, you malloc something, and you didn't free it. Well, I'm going to free it, and I'm going to set the pointer equal to null, not realizing that later on is going to be an access to that memory location that I'm pointing to. And all of a sudden, now I'm crashing. So you are effectively embedding this statement into a big old program inadvertently. Okay? It's not expected behavior. Okay. Whether or not that code's reliable depends on what the definition of reliability is. Okay, so here is a definition of reliability that I want you to memorize. Not for midterm 1. Midterm 2 is a good candidate. Okay. The reliability of a system is a measure of the success with which it conforms to some authoritative specification of its behavior. Okay, is that program that I gave you on slide number 1 reliable? According to the definition, what do we need? Okay, can somebody translate that into, more human English for me, please? What is an authoritative specification of a program's behavior? Tell me what the thing's supposed to do. I can't tell if it's doing what it's supposed to do without knowing beforehand what it's supposed to do. Okay, so you have to clearly say the program is supposed to run. It's not supposed to crash, or it's supposed to run in a non-crashy way. It's supposed to run without segfault. Okay, you have to have some way of saying this is what the program is supposed to do, and then you have to compare what the program does with what it's supposed to do. Okay, reliability implies this comparison between what the program's behavior is and the authoritative specification of what its behavior should be. Okay. When the behavior of a system deviates from that which it is specified for, it's called a failure. Okay? So when your program crashes, if your authoritative specification of its behavior indicates it's not supposed to crash, then we'd say that your program's failed. You're going to need to know what a failure is. So when there are 4 areas of failure. We're going to talk about these guys. 4 areas. Number 1, inadequate specification, design errors in software, hardware errors, communications. Okay? So this is kind of obvious. You know, if your reliability is defined as a comparison of the program or your system's behavior against an authoritative specification of its behavior, if the spec's wrong, well, obviously that could lead to failure, because when your spec deviates from what your program should really do and your spec's wrong, that'll lead to problems with reliability. Likewise, if you went through the design process and cooked up the quote-unquote authoritative specification of a program's behavior, and that authoritative specification is itself incorrect, that will lead to an incorrect implementation of that behavior. Okay? Software, hardware, or how things talk. Okay. So we're going to define the term error. Error is defined as the cause of a failure. Okay? So the failure is when a program deviates from its specified behavior. Error causes that deviation. An error is a deviation from internal state. You don't externally observe an error. An error happens, something breaks on the inside of your system. We kind of think about the system as a black box, and it blinks LEDs, or it flashes, or it sends some communication out, or it, it does whatever it does. Internally, something messes up, and that later on causes us to see, oh wait, I'm sending out a bad signal. My LEDs are flashing red, 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 blue instead of red, blue, red, blue. Okay? So when I am able to observe the error, or the result of the error, that's called failure. That's when the system observably deviates from its behavior. An error is an internal deviation. So something happens on the inside that causes or that leads to the failure. Okay? The cause of the error is termed fault. Okay? So inside you have something that messes up. The cause of that mess up is called a fault. Okay, fault causes an error. Error leads to failure. You can have a failure in a component of a system that causes a fault in the system. Okay? So we can see a system as a composition of a bunch of components. You can observe failure in one of the components of your system. That could cause a fault in the system. The fault in the system causes error in the system. The error in the system leads to system failure. So you have this chain where you got a fault that leads to an error, that leads to a failure, that leads to a fault, that leads to an error, that leads to a failure, and this cycle can continue and propagate throughout your system. Okay, 3 types of faults: transient fault, intermittent fault, and permanent fault. We'll define each one of these. Okay, transient fault. A transient fault starts at a particular point in time and exists in the system for a period of time and then goes away. Okay, so for example, some hardware components could have can be adversely affected by radioactivity. You see this in space-based implementations where you can have like a bit flip introduced by maybe a solar flare coming in. You can see this in, so anyway, what it says, radioactivity. Okay, faults in communication systems are transient in nature. So you're communicating something weird happens, it just happens once, and it only happens for a little bit of time, and then it goes away. Okay. Permanent faults, this is where something breaks, where you have a fault that gets introduced into your system that stays in the system until it's repaired. My cell phone has a permanent fault, unfortunately. The keyboard is dead. Long live the keyboard. Okay, so it has some problem with it that caused the keyboard not to be able to receive me typing anything on it. I can't push any buttons. I can't turn the phone on. I can't turn it off. I can power it up. I can PC link with it, but I can't do anything with any buttons. So therefore, I'm getting a new cell phone. Should be here tomorrow. My cell phone has a permanent fault. Intermittent faults are kind of like a hybrid in between a transient and a permanent fault. With an intermittent fault, you have a transient fault that manifests itself and then goes away, then can manifest itself sometime later and then go away. It occurs from time to time. So you can see an intermittent fault, say for example, if you have heat-sensitive components, and that component runs, heats up, and so you have a fault, something gets shut down, and all of a sudden the part cools down, starts to work again. You say, hey, everything's great. You start to run things again. It heats up again. You have the fault, and this cycle repeats. So that's an example of an intermittent fault. Okay. Yep. Mitch.
The difference between transient and intermittent is just that transient one lasts longer?
So the difference between a transient and intermittent fault is that a transient fault, it occurs, it lasts for a little bit, and then it goes away. It doesn't come back again. Okay? Intermittent fault is that same thing where it occurs, lasts for a little bit of time, goes away, then it'll occur again, lasts for a little bit of time and go away, then it'll occur again, and last for a little bit of time and go away. So it's just the repetition of that fault. Okay? So when we're looking at categories of failures, so permanent, intermittent, and transient are categories of faults. These are categories of failures. How can your system fail? Two ways, two general categories: value failure, timing failure. Value failure, so we're supposing that your system produces some value, or it does something. If it does the wrong thing or produces the wrong value, then we're saying it's a value failure. If it delivers some service correctly but at the wrong time, that's a timing failure. And this has big impact on real-time systems. So if your system produces the correct results but at the wrong time, and that violates some time constraint, then you can end up with a timing failure. So here's a diagram of various failure modes. So again, you can have a failure that occurs in the timing domain or in the value domain. In the value domain, we have subcategories: constraint error or a value error. Okay, so the previous slide explained the difference between a constraint error and a value error. With a constraint error, you have maybe it's producing a value, but it's outside of some range. Value error is where a constraint error doesn't apply. Okay. Timing domain, you can end up delivering a service early, you can deliver a service late, or you can just not deliver a service. Okay. So all of these guys are not that you're delivering the value that the service produces incorrectly. What you're doing is you're just delivering it at the wrong time. Wrong time can be early, late, or never. Yeah, Jonathan. In some systems, so if you bring it early, sometimes some systems, yes, it is incorrect. So if you start to apply your brakes too early. Okay? So all that we're doing is we're just codifying and classifying the various ways that a system can fail. Some systems, the delivery of a service early is not going to be a problem, but other systems it will be a problem. So omission has subcategories. You can fail silent, you can fail stop, or you can fail controlled. And we'll talk a little bit more about these guys in subsequent slides. Okay. How do you achieve reliable systems? There are two ways that we deal with this. We call them fault prevention and fault tolerance. So the first one is just make sure your system never breaks. Right? So never have your system break. That's like saying never put a bug into your program in the first place. Y'all are good with that, right? You can make sure you do that. Yeah. Okay, yeah. So we do this as much as we can, but obviously it's not possible to do completely. Fault tolerance. Fault tolerance is where we recognize the fact that we're going to do as much as we can on preventing faults, but we are going to end up having to live with the fact that our system may end up messing up at some point. So we put in and deal with faults explicitly. We don't put in the faults explicitly, but we put in code and infrastructure inside our system to explicitly deal with faults as they occur. And this is fault tolerance. Okay, so fault prevention. We'll talk a little bit about fault prevention. Okay, so we have two stages of fault prevention. It's called fault avoidance and fault removal. Okay, so with fault avoidance, the idea is let's not be impacted by the fault at all. So we limit the introduction of faults. Various techniques here that we employ. So first off, we consider our system as being composed of components. when we're composed of components, what we want to make sure to do, the first best thing that we can do is, don't use cruddy parts when you're building a system. So you want to be able to use the most reliable components that we have, such that our performance specs are met. Okay? We want to use thoroughly refined techniques of interconnection for those components. So in other words, use the best components you have, and use well-defined and well-documented ways of hooking things together. Make sure you apply appropriate packaging in order to screen out expected forms of interference. So this would be, make sure if you're going to be producing a lot of heat, and heat might be a problem, make sure that your packaging supports heat dissipation. Okay? Or if your system is going to be sensitive to noise, make sure you apply an appropriate amount of shielding to prevent noise from impacting your system. Okay? Rigorous, if not formal, specification of requirements. So again, this goes back to that definition of what is reliability. We compare the system behavior against an authoritative specification of what it should do. Okay? Requirements analysis is critical when you're doing system design, especially safety critical systems, systems that are required to be highly reliable. So you want to do rigorous specification of requirements, so you know exactly what is this system supposed to do. And you don't just say, well, I want it to kind of work. Kind of work is kind of ambiguous. Okay? So what we have to do is exactly say what we mean, and we try to say exactly what we mean in an unambiguous way. And when we say it in an unambiguous way, oftentimes it requires mathematics to formulate what do we mean when we say we want the system to do this and this and this and this. There are formal mathematical approaches, or formal approaches based on mathematical rigor, mathematical semantics for capturing requirements and specifying system behavior. Okay? There are various techniques out there, and different techniques have been studied for doing this. One technique is called communicating sequential processes. This is a process algebra. It's a means of modeling concurrent systems where you've got processes that interact with each other, in a multi-process system. So you can model various behaviors as a set of processes and their interactions. CSP allows you to capture those requirements as a set of processes and their interactions, and then it also allows you to apply formal checking against that specification. So you can supply this specification to a program called a model checker tool, and you can say, I want to make sure this never deadlocks, and I want to make sure that this process is able to complete this action, and I want to make sure I never see this process run at the same time that process is running. So you can feed it a few checks that you want it to do, and it'll formally prove that under no circumstance will this ever happen, or I guarantee that under all traversals through the behavior of this system, this will happen. And it's much more thorough and exhaustive than simple testing that you can perform on a system implementation, and it occurs at requirement specification and analysis phase, as opposed to down in the depth of testing your system after you've built it, so you can catch errors much earlier. Use of proven design methodologies. So one time I went over to SmallSat. This is this conference that they have here that you get a whole bunch of industry and academic representatives presenting their work on composition of small satellites. And I went and talked to some of the vendors of hardware for satellite platforms. This is my first year here, and I talked to some of these vendors, and I said, well, what do you do when you're dealing with these embedded systems, and how do you guarantee you're not going to have concurrency problems? And they said, oh, we use a real-time operating system. And I sat there and I waited for them to say what else they did. And they were done. They just said, well, we use a real-time operating system, and that takes care of all the concurrency bugs. Well, you guys will be able to appreciate that fact more at the end of this class, but that is such an ignorant statement. Just using an operating system that allows you to do threading and minimizes the latency of the operations the operating system performs does not guarantee you bug freedom when it comes to processes and their interaction. So basically these companies were ignorant of the fact that they needed to explicitly deal with concurrency in their system implementations. So we just have a real-time operating system. That's what you call a lack of formal, proven design methodology. They're not designing for concurrency. You have to employ proven design techniques. Okay. Use of languages which facilitates which have facilities for data abstraction and modularity. So I've beaten on this one a whole bunch. Y'all ought to know about data abstraction modularity thus far. We use C, which kind of violates this principle of using a language that has facilities for data abstraction modularity. You can do abstraction and modularity in C. The language doesn't have direct facilities to support this as much as it should. So, where possible, if you want to guarantee reliability, you should probably be using a language that better supports constructs to support these types of structures. Okay. Software engineering environments. These are tools, design tools that let you that support your efforts in doing system design. Okay, fault removal. So that was fault prevention. What techniques can we do to remove faults? Okay, so we try to avoid the faults, but despite our efforts to avoid the faults, design errors in both hardware and software components will exist. What do you do to remove the faults? So the idea is, what we want to do is find and remove the causes of the errors. This is typically performed at design time when we're talking about fault prevention. How do you remove the errors? Well, you have design reviews, program verifications, code inspections, testing. You have a framework set up and a process set up whereby you can evaluate the design at design time before you actually deploy the system. Once you're dealing with fault removal after the system has been deployed, that's more in the region of fault tolerance rather than fault prevention. But you want to make sure you're thorough in the analysis of your design beforehand. Have a whole lot of eyes looking at it, independent teams looking at it. So system testing can't ever be exhaustive and can't remove all your potential faults. All that you can do with a test is show that a fault exists. You can't prove that it doesn't exist. You can conjecture multiple ways that a fault could potentially manifest itself, but you can only test for specific cases. You can't exhaustively prove the absence of a fault. That's where model checking and exhaustive state space exploration with formal analysis comes in, where you can do a better job of proving the absence of an error. Okay. Where does fault prevention fail? Well, basically, you're going to have bugs. They're going to creep through. You can't test for everything. You can't prove that your system is completely bug-free. Sometimes your system encounters states that weren't considered by the designers. So consequently, you're going to end up having a system that will end up with bugs. So we want to be able to implement and deploy fault tolerance schemes. The last slide talked about one reason why you may want to deploy fault tolerance. Could be like a spacecraft that's orbiting the Earth that has no crew on it. You want it to be able to fix itself to some certain degree, or to respond to errors, or to be tolerant to errors, so that when they occur, it doesn't cause the system to break. Okay, levels of fault tolerance: full fault tolerance, graceful degradation, fail safe. Okay, full fault tolerance is where we attempt to say this system can react to whatever fault that occurs and will never stop functioning. Good luck. Graceful degradation. This is called fail soft. So the system will attempt to react appropriately to any fault that can occur, but there are times where you cross the threshold of where it can't really tolerate any more faults, so it has to start disabling some of its features. So fail soft is where you start to disable non-essential features and you keep the system alive. Again, in the context of a spacecraft, if you have a spacecraft that conducts science experiments and you all of a sudden have a loss of a battery, or part of your battery is no longer able to accept a charge, what that means is you don't have enough power to run everything on the spacecraft, so you turn off your science instrument in favor of keeping the spacecraft alive and in orbit until maybe somebody later can come up and fix it. Fail safe. This is where you try not to kill people as the system fails. Okay, so you want to make sure that the system maintains its integrity while basically halting and trying to reboot itself. Okay, so fail safe is don't hurt anybody and don't hurt the system itself as you attempt to bring yourself down into a failure mode. Okay, a key component of fault tolerance is called redundancy. So redundancy is where you do extra things. You either add extra hardware or you check things extra amounts of time in order to, or an extra number of times, in order to detect whether or not a system fault has occurred and how to avoid it. Okay? So we often call this protective redundancy as we add extra stuff, and that's built in there in order to protect the system. Okay? One consequence of having redundancy is you're increasing the footprint of the system, maybe the power consumption. It definitely impacts your bottom line. Okay? Okay. Two types of redundancy, static and dynamic. Okay? Static redundancy is where you add stuff to the system, where you're adding extra hardware or extra software. You're physically replicating components, physical replication of hardware, physical replication of software. Dynamic redundancy is where you do checks multiple times at runtime. Okay? The way that static redundancy is typically implemented is what we call triple modular redundancy. This is more for hardware. So triple modular redundancy is where you've got a component that potentially could have a fault in it. Any component in your system could have a fault in it. So what we're going to do is we're going to have instantiated in the system 3 replicas of that chunk of hardware. And they'll all do their thing. They'll all produce a value. And then you take the 3 values that are produced and you send that to a voter unit. This voter unit will take majority rules and will detect whether or not all 3 of them vote the same way, or if 2 of the 3 vote the same way. If 2 of the 3 or all 3 vote the same way, the result is what majority says. This can detect if any one of the modules observes a fault. So if it observes a fault, the idea is that it will be observed in the value that it outputs. So if it deviates from what the other 2 are saying, we know that that one system is faulty, the other 2 are working fine, so we ignore that one system. The problem where this happens is if you have more than one component, you get a fault. So you can only detect one fault with this. You can, if you scale this up to NMR, where that's N-way modular redundancy, you can detect more faults. Okay. Dynamic redundancy is where you supply inside it's supplied inside a component, and it indicates the output is an error. So basically, this is like where you've got a checksum or a parity, where you are supplying extra information and doing an analysis at runtime to determine whether or not you've got an error. So, software fault tolerance, we can also do redundancy in software. This is called inversion programming. Dynamic redundancy, we'll talk about these guys are recovery blocks, backward error recovery, exceptions, which are forward error recovery. Okay. Inversion programming. You know, this is analogous to triple modular redundancy. But in software, if you're trying to detect the presence of a software bug, and you just take one program and you run it 3 times, if you've got a bug in your program, all 3 copies are going to have the same bug. Okay? So what you do with inversion programming is you don't have 3 copies of the same program, but you implement the program 3 different times. And the whole idea is if you have separate teams in separate locations and each with the identical set of requirements, but no communication going on between these teams, the idea is that the probability that each team will make the same error, assuming the specs are correct, will make the same error in the same location of the program is very low. So with inversion programming, we have 3 different versions or n different versions of the program or of the software module that we're considering. Each of those modules are separately implemented, and hopefully, you know, we acknowledge the fact that each of them may have bugs in it, but hopefully the idea is that the bugs will be at different spots, and they'll be observed in different ways. So the idea is that we take the results of the replicated programs, we send them to a voter, again, majority rules, and then proceed from there. Okay? So inversion programming is how you do software-based redundancy. Here's a diagram of it. 3 different versions. They have a driver program. This driver program invokes those versions. The driver programmer sees, so each version sends a vote to the driver, sends status information back to the various versions. The driver does the voting and passes the information along. Okay. We're going to skip over that. This is just saying that in order to do inversion programming correctly, you first have to have an initial specification that's correct. Because if you have an invalid specification, all your programming teams are going to implement the same problem. each team has to be independent. You maybe want to have them on separate continents. You maybe want to have them using different programming languages. You want to make sure that they can't communicate with each other, that if there's clarifying questions that they need to ask, they ask the spec writers, not the other team, because you want to make sure that the probability that each team makes an error, you want to make sure that the probability that each team makes the same error is reduced to as low as possible, and that's contingent upon the independence of the efforts of the team. In practice, this inversion programming must be performed in a context where you supply enough money to carry it out, so you have to have management buy into it. Okay, so software dynamic redundancy. You have 4 phases to this. Error detection, damage confinement and assessment, error recovery, and fault treatment and continued service. So we'll talk about each one of these guys. But these go in steps. First, you've got to detect your error. What you've got to do is figure out, once you've detected the error, how bad is it? And once you've figured out how bad it is, you've got to recover from it, and then keep on moving on, fix the problem. Okay, so what is error recovery? Okay, so error detection, those other phases are pretty important, but error recovery is arguably the most important of those phases. There are 2 techniques to do error recovery, forward error recovery and backward error recovery. Forward error recovery says, okay, I encountered a problem, I'm going to skip it and go on. Okay? Backward error recovery is where you're doing checkpointing, where you save some state and you say, oh, I encountered a problem, let me go back, try to rerun this, see if I can kind of avoid what the cause of the problem was and move on. Okay? All right. So backward error recovery involves saving a checkpoint and then jumping back to the checkpoint when you're detecting an error. So here's an example of a problem that can occur when you're doing checkpointing. So BER stands for backward error recovery. P1 and P2 are different processes, and let's suppose that each process sets its own checkpoints independent of each other. So it goes along and it decides, I'm going to set a checkpoint so that in case later on I encounter a problem, I can go back to my checkpoint. So these are timelines where time progresses from the top of the screen to the bottom. And let's suppose that down here at the bottom, where this labeled T error, is a time where an error occurs. Okay? So when an error occurs, that each process is going to be notified that there is an error, so they will both back up to their most recently saved checkpoint. P1 will back up to R13. P2 will back up to R22. Here's the problem with this. Whenever you back up across a time where you had an inter-process communication, because there's an error here, and I'm backing up to this location on P2, this R22 location, and I'm crossing the boundary of when an inter-process communication occurred, I'm going to have to repeat that inter-process communication, and because I'm going to have to repeat it, I need to make sure that the guy that I talked to backs up to some point before that inter-process communication. So I back up to R22, and I send a message over to P1 and tell him, by the way, I undid IPC4, so you need to back up to some time before IPC4. So P1 goes from R13 and says, oh, that happened before this recovery point, so I need to back up even before. So he backs up to R12. But we've got IPC3 that happens between R13 and R12, and so he undoes IPC3 and then notifies P2. And P2 says, oh, that's before my recovery point, so I'm going to recover back up to R21. Oh, we've got IPC2 here that needs to be undone, and so we notify P1, and P1 has to back up and backs up to R11. Oh, we've got to undo IPC1, so that makes P2 have to undo back, and we're back at the beginning of the program. So this is called the domino effect, where because of the fact that you've got all these inter-process communications going on, it eventually causes both programs to need to roll back up to the beginning of the execution of the program. Okay? Yeah. Yeah, so that would be what's called a recovery line. So you can just force everybody in the system to all do a checkpoint all at the same time, and that will prevent you from doing this ladder backwards in time. Okay. Fault treatment and continued service. Well, error recovery, you can, effectively with error recovery, return the system to an error-free state and begin to execute again. But the whole idea is we have a problem here. Something caused the problem. If we can localize the problem, we want to be able to fix it so that we don't encounter that problem again. So how do you go about fixing a software bug as your program runs? Do you want your satellite to do that? So that would require your software on your satellite that's running autonomously to run GDB by itself, figure out what the bug is, and then dynamically adjust the compiled program to not have the problem anymore. I don't trust software at all. I really don't want to trust it to debug itself. So this whole having an autonomous program repair itself is touchy. So this is not done very often, where you can figure out how to instruct your software to repair itself. Okay, this is recovery blocks. Basically, this is just, there are some programming languages that have language-based support for the checkpointing mechanism that we talked about. So you can have an acceptance test that says whether or not, so you get into a recovery block, you execute a block of code, you have an acceptance test at the bottom. The acceptance test determines whether or not the block executed correctly. If it didn't, you go back up to the top of the block and execute again. Inversion programming versus recovery blocks. I'll post the slide. You can look at the slide. Okay, dynamic redundancy and exceptions. So you also have forward error recovery, where forward error recovery is defined as exception handling. We're going to have a whole chapter on exception handling, but basically this is where you encounter an error and you jump over it, as opposed to jump back and re-execute the code. And most of the programming languages that we deal with do forward error recovery as opposed to backward error recovery. So exception handling, when you use try, catch, and throw in C++, are examples of forward exception handling. So we're going to beat on exception handling to pieces. So we'll skip some of that. Safety and reliability. These are just some more terminology that we want to define. Safety, freedom from those conditions that cause death, injury, occupational illness, damage to or loss of equipment or property or environmental harm. Are my tests safe? Does it lead to freedom of death, injury, occupational illness? Anyway. Mishap, unplanned event or series of events that can result in death, injury, etc. Hopefully my test is not a mishap. Reliability, we've already defined that. Okay. Safety is the probability that conditions that can lead to mishaps do not occur whether or not it is intended. We'll define this and talk a little bit about safety next time. All right. The test will be up in 10 minutes. Good luck with it. I have office hours today. 3:30 to 5. What's that? Yeah. It would have been much better to check if I had my phone. That should be remedied either this afternoon or tomorrow. Lab 4, oh yeah. Oh, one other thing, guys. Semester-long board checkout is now available. So you, one member of your team can check out a board for the semester, or your team can check out one board. Don't check out multiple boards per semester. Don't drop your laptop either. Okay. The other thing is I forgot to post Lab 4 on Tuesday. It's now up. I changed the due date so that you can have an extra Tuesday. The tablet was never the problem. It's the power cord. Just replace the power cord.
Like our lab, right? That part.
Go home already?